So we have this chess state, and I'll be drawing it as a tree, just like we draw tic-tac-toe, where each one of these circles is a chess state object. And by the way, if you want to do it in C++, I provide that to be my guest. If you want to translate this into your favorite language, even cooler, but I'm not doing it for you. So there you go. The chess state object can answer questions like, is it white? Or you can set a piece on the board. And it returns a heuristic. So the standard heuristic in chess is that queens are worth 9, and bishops are worth 3, and knights are worth 3, and rooks are worth 6, and pawns are worth 1. You're slightly familiar with that heuristic? Anybody never played chess before? Okay, cool. Well, you're going to kind of learn chess, maybe. Although, truthfully, you can do this whole assignment without even understanding what you're doing. You can just implement alpha beta pruning and just watch it play and say, that must be chess. So you don't really need to learn chess. But it's one of those life skills you probably want to pick up on because a lot of people know chess. It's a very standard game. Okay? It's very common in chess to add those pieces that way. Some people have gotten so standardized on it, they think that's the right way to score chess. So just to be obnoxious, I made up my own scoring system, where a queen is worth 88, and a bishop is worth 36, and a knight's worth 31, and a rook is worth 63, and a pawn is worth 10. You can see it's almost the same. But I decided to tweak it a little bit because I like bishops slightly better than knights, sometimes. I think an even more intelligent heuristic would value knights a lot early in the game and bishops more later in the game, or something like that. Or maybe it's vice versa, depending on the layout. And yeah, people do nitpick over the best heuristics and how to implement the thing really well. If you want to mess with these numbers, awesome, be my guest. If you don't, that's fine too. You can just leave it and it should just work. So incidentally, let's suppose you wanted to know, are these heuristics better or worse than the standard heuristics? How would you do that? Yeah, exactly. So put a Boolean value somewhere, or compile it twice, or make some way that one of them uses the standard heuristics and one of them uses mine. Play chess against each other. Play 30 games. If this wins 16 of them, then you can say, hey, maybe it's slightly better. Probably have to do 300 trials to see which one's really better. Yeah. So plug in a genetic algorithm to mess with your heuristics, and then battle them against each other to be the tournament. And then this thing will evolve the best heuristics, let it run for days, then publish a paper saying, I've found the new world's best chess heuristics. And you'll find out that this 88 changes to an 87, and then you have reached chess awesomeness. It just sums up how many pieces you have and subtracts how many pieces your opponent has. I think it always scores white as positive and black as negative. So if you're the black player, you're the minimizing agent. If you're the white player, you're the maximizing agent. But here's the cool thing about using an AI. Obviously, you could sit there and implement a whole bunch of rules, but that's dumb. Wouldn't it be cool if you could mess with the rules and it would still play well? That's way awesomer, isn't it? So when I play with my daughters, in fact, just yesterday I was playing with my daughter, we always mess with the rules of chess. And the great thing about it is it hurts our brains because we're always playing a game we don't fully understand, and that really makes us think. We played, last time we played was your pieces could pass through your own pieces, but they couldn't pass through your opponent's pieces. Totally changed the strategies. Everything we're used to doesn't work the way it used to, and now we had to play totally different, and it really changed things. So, one time we played toroidal chess where the board wraps around sideways, so you can move your bishop diagonally sideways and come in the other side and get them in checkmate that way. That was lots of fun. Lots of our variations have turned out to be really dumb. Like we had one where you could bump your pieces forward a space by ramming them. Anyway, you don't care how I play chess. The point is, I could code these things up, and alpha beta pruning could play all of them, and I wouldn't have to write a line of code to change it, except all the lines of code to explain the rules to my alpha beta pruning. But it really should be general purpose. If you were to code up, under these conditions, do this, basically a reflex agent, that's dumb, and that wouldn't be doing the assignment. I have here an iterator called chess move iterator, Guess what it does? You use a chessboard, and you specify whether you're iterating over white's moves or black moves, and it returns a chess move iterator, which I have defined somewhere here. And a chess move iterator tells you, has the has next and the next, and for each next, it returns a chess move. A chess move has a XY and an XY. Here's where you were and here's where you're going. Does that make sense? So you're basically taking the piece on C2 and moving it to D3. Except in this case it's 0 index, so it's going to be 0 to 7, 0 to 7, 0 to 7, 0 to 7. All right. So given any board, you can call the iterator to get a chess move iterator, which will return a bunch of these that will tell you all the possible valid legal moves to Schmess. And then you'll implement alpha-beta pruning to sweep through all those possible boards until you find one that returns a good heuristic value. After you've searched to the depth, you'll call heuristic to say how good is this state, and that's all you need. The next thing to talk about is alpha-beta pruning and how it differs from minimax. So in minimax, we play the game all the way to the end. We calculate the min of the max of the min of the max of the min of the max to find out what's the best move. Why is that the thing to do? And under what conditions is that the thing to do? When do you use minimax as opposed to, say, uniform cost search? Why are we doing minimax? In uniform cost search, you were the only player, right? In tic-tac-toe and chess, there are now multiple players. That's one of the differences. Why does a player make a difference? There's uncertainty, but there's also intelligence in them. And actually, uncertainty is a little different than intelligence, because with uncertainty, you can marginalize it away, right? So if we were doing utility theory, we would just say there's this much probability that you do that, this much probability that you do that. And you can do the same thing with intelligence, but depending on how intelligent it is, it gets increasingly difficult to assign probabilities to it. Let me put it this way. If your tic-tac-toe board looks like this, you have two moves. Obviously, if you're X or O, no matter what, the intelligent move is to go in this spot, right? Okay, and not to go in this spot. And how do you know that? Because you're going to do what maximizes your best interest. Well, let's suppose we're one move behind. Do we know what your opponent is going to do? Depends. If we know your opponent is intelligent, then we could assume that the strategy you're doing is the same strategy they're going to follow. And you know there's only one thing you could do here because you're not stupid, right? I should say because you are intelligent, to be positive. Well, by the same right, you don't need to marginalize away what your opponent does. There's not possibilities. It's not that your opponent is going to treat these all as equal probability, or if you assume your opponent is intelligent, that's going to be the best thing you could do, isn't it? Because imagine if you do something that isn't assuming your opponent is intelligent. What's an intelligent opponent going to do? Exploit you. It's like, oh, you didn't assume I was intelligent. Well, now I'm going to act intelligent, and then you're dead. So you have to assume your opponent is intelligent because they might be. And thus, the intelligent thing to do is to assume that your opponent is intelligent. Does that follow? Is minimax optimal? Yeah, so let's assume it's not depth limited. We're going to play all the way to the end. There's no heuristic involved, so we can wave away that aspect of non-optimality. Is minimax optimal? Well, like always, it depends on your definition of optimal. So it's optimal given the assumption that your opponent is intelligent, but that's not always true. What if your opponent is unintelligent? Well, if your opponent was unintelligent and you knew that, that's significant, then you could exploit that. You could say, oh, hey, I know you're not going to see this, so I'm going to go here. And then you can, so I could move my queen somewhere where my queen could get killed, but if I know my son's not going to see it, I can exploit that and then have him in checkmate in the next move, right? But if I were playing a chess grandmaster and I tried the same thing, he'd see that coming and slaughter my king, so I can't exploit that. So in that sense, minimax is not optimal because minimax assumes you're playing a chess grandmaster. Yeah, so is minimax optimal? In a sense, no. But usually if your opponent is not going to play well, you don't know that, right? Or at least you don't know how they're not going to play well. And so it becomes somewhat unexploitable. And therefore, you kind of assume that the best way to play is assuming that they're going to play as well as possible. So in the sense of you don't know how your opponent's going to play, you should assume that they're good, it is absolutely optimal. It's kind of the best strategy you can follow in any two-player situation. So it's kind of if I asked is it optimal on a test, I think the answer you should give is yes, because I don't think there's anything that could be called more optimal than Minimax, unless it had more knowledge, in which case, yeah, absolutely, pure utility theory is the answer. And this kind of is pure utility theory with the assumption that your opponent is intelligent. So given that we have this thing that we're calling optimality, how can we achieve the same level of optimality without doing so much work? The answer is alpha-beta pruning. Do you remember when we did uniform cost search and we said, this is optimal? Then we did A* search and we said, this is optimal too, but it's better. That's what we're doing now. Minimax is optimal. Alpha-beta pruning is the exact same thing. It produces the exact same results, but it does less work. And so we're going to talk about that. You can improve upon alpha-beta pruning even by being suboptimal. There are things you can do that don't involve exploring the whole tree. And so you could compare that to genetic algorithms. And that's actually what AlphaGo ends up using. So they don't do pure alpha-beta pruning. They do something very much like it, but they also use some heuristics to intelligently search good branches of the tree. And it's not provably optimal anymore. So it's not as good of a Go player as it would be as if they let the computer run for trillions of years that it would take to do pure alpha-beta pruning. But it ends up being better because, hey, it finishes in our lifetimes. So we're kind of at the A* stage now with alpha-beta pruning. It's still optimal. We're seeing how far we can go and still be optimal while saving computational costs. So let's look at alpha-beta pruning. Just given the title, can you infer anything about how alpha-beta pruning works? Yep. It basically does Minimax, except under certain conditions it says, hey, wait, I don't really need to explore that branch because I know it's not going to work out. So it just doesn't. And it's still optimal because it only prunes branches that definitely aren't going to work out. So let's look at how that works. There's an example here. And I don't know if it's a great example, but it's an example. Let's do it. Plus, it's accessible on Wikipedia, so it makes a nice, convenient one to, if you learn this one, it'll be there as long as it's there on Wikipedia, and it will always be in the history. So I think these are good examples to work with. The nodes marked with two little red crosshatches there are the ones that will be pruned by alpha-beta pruning. How much time does that look like it saves you from evaluating this tree? Yeah, so it's kind of hard to tell on this tree because you're still evaluating 80% of the nodes here. But also note that this tree only goes 4 layers deep. 1, 2, 3, 4, or 5, depending on if you count the first one. In general, if you have a tree that goes very, very, very deep, pruning makes a pretty darn big difference, and it ends up saving you a lot more than half of your computation time. So I don't think the proportions you're seeing here are representative of what alpha-beta pruning tends to do, but the example certainly shows cases of how to tell when alpha-beta pruning is going to prune. Okay, let me talk you through why these are the branches that are pruned and why the other ones aren't. And let me describe alpha-beta pruning first with an example. This is Eeyore. He's sad. Hold that picture in your head. That describes alpha-beta pruning. So imagine Eeyore is doing alpha-beta pruning, and he's walking through this tree, if I can find it again, and he's going down here, and when he reaches this 4 here, and he says, should I even go down that 5? Then he says to himself, why bother? They'd never pick me anyway. If you can say that, and it makes sense to say that, then that's when alpha beta pruning prunes the branch. Okay? Now, having kept that in mind, let's walk through the tree and see why we have to search them all. In fact, before I do that, let me back up, push that on the stack. I got to talk about different ways of searching the tree. When we did breadth first search, we were doing a breadth first traversal. Well, that's kind of obvious and dumb. Breadth first does a breadth first traversal, because it is breadth first. How do you do a depth first traversal of a tree? Yeah, if you implement it recursively, it's going to do depth first. If you implement it, how do you implement a tree search in a breadth first manner? You make a queue, you put the first one in the queue, you pop something out of the queue, and then you push everything that comes out of it into the queue, and then you keep going. When you use a queue, it makes a breadth first traversal of a tree, right? If you use a stack, if you just take a breadth first implementation and you swap out the queue with a stack, what does it do? It does depth first search. And when you implement it recursively, it does depth first search. Why? Because it uses the stack as a stack, right? It depends on whether you count the node when you're returning or whether you count it when you first visit it. You can actually do either with a stack. When we look at the minimax algorithm, or alpha beta pruning, you'll see that it is a recursive algorithm, but I don't want you to think that this algorithm must be implemented recursively. You could change it from a recursive algorithm to one that uses a stack, and it would do exactly the same thing. It's just you wouldn't be using the implicit language stack, you'd be using an explicit stack instead, right? And you could swap that stack for a queue and turn it into a breadth first traversal, and it would still be the same algorithm. It would just evaluate in a different order, and it would come up with exactly the same answer, as long as you search the whole tree, right? Okay, so please don't think this algorithm must be depth first. There's nothing about that. It's just that recursive is a really convenient way to write it in very few lines of code. So we're doing the same algorithm we did in breadth first search and uniform cost search. It's just we're going to switch a queue for a stack now and do it in a depth first manner. And because we're doing it with a recursive style, it'll feel like a totally different algorithm to you. But in your heads while you do it, I hope you're thinking, this is the same dumb algorithm from yet another perspective. Dr. Gashler's just teaching the same algorithm over and over and over with new pieces tacked on. You see that? Okay, so good. Let's learn this same algorithm yet again. I should just call this algorithm intelligence or something like that, because it's pretty much the only thing we do in AI.